In this video, we're going on a short number journey, and just to get the disappointment out of the way early, I've not yet traveled the last leg. We're going to start with a kind of small number, 64, visit 3 important large numbers along the way, and then define my mega fave number. So a quick motivation for starting at 64. I like to make things, and I was on a kick making dissection puzzles, like the popular Summa cube and the Bedlam cube. I made a pentomino chessboard, and then I made a 3x3x3 snake cube. After that, I thought about the 4x4x4 snake cube. This, of course, is where 64 comes in. Some of you are probably thinking the same thing I was. Hey, 64 also showed up in your chessboard. And the idea was born. Could I make a snake cube that could also form a chessboard? In short, yes. I was able to find an arrangement that works. I was even able to arrange the board in pieces in such a way that the board could be playable with nice smooth edges, but also house the pieces inside when it's in its cube form. But now come the big numbers, because my inner mathematician asked, how many unique snakes have this property? The snake makes a square and a cube, so the number of cubelets, the little cubes that make up the snake, must be a perfect sixth. The first two are trivial, 0 to the sixth, the null snake, and 1 to the sixth. There's only one unique 1 cubelet snake, and it forms 1 square and 1 cube. Finally, we get to 2 to the sixth, and things get interesting. I'm sure 3 to the sixth, 729, and up are also interesting, but they're also a lot bigger than I can deal with, both for physically building a snake and for enumerating. Back to 64, 8x8, 4x4x4. Here's how we start getting some big numbers. How many unique 64 snakes can one make? I'm going to need to define what I mean by unique. We have at least 2 options here. If you're using chessboard coloring, then your snake is directional. It has a defined head and tail. This is the easiest to count. Every snake of 2 or more cubelets has 2 invariant end blocks. All the cubelets that aren't ends can either be straight or turn pieces. Here are all the 6 snakes. Therefore, a 64 snake can take any of 2 to the 62 forms, or a bit over 4.5 quintillion. Without coloring, undirected snakes, we need to remove some duplicates. You might notice we have 2 types of snakes, one with partners, the same snake but in reverse, and those without partners, which I call palindrome snakes. Noticing this makes our counting much easier. How many palindromes do we have? Let's think about our choices again. I'm going to focus on even-numbered snakes and leave the odd for you as homework. As before, the first cubelet is invariable. The second and up to the midpoint can each be straight or turn. So for our 64 snake, that means 2 to the 31 options so far. But once we cross the threshold to the back half of the snake, we don't have any options anymore, because it must match its palindrome position partner. So for our 64 snakes, we have 2 to the 31 palindrome snakes with no partners, and 2 to the 62 minus 2 to the 31 partnered snake, half of which need removed. Therefore, we have a little over 2 quintillion undirected 64 snakes. So our first number of interest in 2 forms is the number of unique 64 snakes. Directed, about 4.5 quintillion. Undirected, a little over 2 quintillion. It'll be clear to many of you that not all these snakes could twist into an 8x8 square, let alone a 4x4x4 cube. In fact, a whole lot of them can't. I'll come back to that. You might also think some snakes can probably make a square or cube in more than one way, and you're right. Our next 2 big numbers relate to how many different ways the 8x8 or the 4x4x4 can be formed using any of the snakes. This leads us to Hamiltonian paths. A path on a graph is Hamiltonian if it hits every vertex only once. Again, we have a lot of options about how we count, or said differently, we can have different criteria for what counts as unique. You can see with our 2x2s, we might care about direction, important if using chessboard coloring, and we might care about orientation. I prefer to ignore direction and orientation, so for me, I would say there's 1 2x2 path, 3 3x3 paths, and 38 4x4 paths. So for our 8x8, rather than Jacobson's number of about 3 billion, I prefer 377,919,174. That's the number of paths ignoring symmetries in direction. I like this because the same physical uncolored snake puzzle could create any of the symmetric arrangements. Many of the snakes that could produce 8x8 squares cannot make 4x4x4 cubes. Many of the snakes are too straight to even have a chance. Removing all 8x8 paths that have 3 or more straight pieces in a row, we drop to a bit over 8 million snakes. For 4x4x4 paths, these authors give us almost 28 quadrillion oriented paths, or just over a quadrillion, discounting symmetries. So finally, my 3 special precursor numbers are the following. Our 64 snakes, about 2 quintillion, our 4x4x4 paths, about 1 quadrillion, and our 8x8 paths, about 377 million. And all this preamble finally leads us to defining my actual megafave number. My megafave number is the number of unique undirected snakes of length 64 that can form both a 4x4x4 cube and an 8x8 square. That number is... well, I warned you at the beginning. I'm not sure yet. Starting with the 8 million plus snakes that form 8x8 squares that weren't too straight, I began testing 4x4x4 paths. I currently have 4,419,004 paths, though I haven't checked to see how many unique snakes it takes to form those paths. My goal is to catalog and map all the 64 snakes that form both 8x8s and 4x4x4s. For example, snake number 1,072,420 so far has produced 4 4x4x4 paths and also 2 8x8 paths. So my megafave number is well defined. I just haven't quite located it yet. Thanks for coming along on the journey.